Hello, everybody. This is Mrs. Wild from your WCA Physics B class, and we are now doing lesson 3, and it's on states of matter. Now, we're not going to get by very long without having to do math, so in this lesson, there's math involved. And your keywords, they should still be somewhat familiar to you guys, but there might be some words in there that aren't. So let's go through them. We have boiling point, pretty simple. Condensation point, temperature at which a gas becomes a liquid. Evaporate, freezing point. And then we have heat of fusion and heat of vaporization. And remember that heat refers to like energy, thermal energy. So this is the amount of thermal energy that must be absorbed by a fusion is by a solid in order to change it completely into a liquid without changing its temperature. And you might be going like, wait a minute, how can you change something from one state to another without changing temperature? But we'll talk about that in a minute. Heat of vaporization. So this is the opposite. This is the amount of energy that is absorbed by a liquid at its boiling point in order to change it to a gas without changing temperature. So just a different state of matter here. Heating curve, which we'll see in a graph as we get through the lesson. A hydrogen bond, which you may have heard of before. These are fairly um, strong bonds between hydrogen atoms. So when you look at certain atomic or molecular structures, sometimes the way in which it's bonded can lead to having like a slight positive end and a slight negative end. And that can end up causing something called a hydrogen bond, which we can talk a little bit about. Intermolecular forces of attraction, melting point, phase change, plasma. Specific heat is another thing that you might not be familiar with. The amount of heat required to raise the temperature of 1 gram of a substance 1 degree Celsius. And it's a very specific definition. And then sublimation is another word you might not be familiar with. And this is a change of state from a solid directly to a gas. You might not be familiar with the word sublimation, but I bet you've seen the process of sublimation before. So it's going to talk a little bit about the different states of matter, solid, liquid, gas, and plasma. And we didn't talk too much about plasma here, other than it's a much higher energy state than like a gas is. I like these diagrams on states of matter. So I want to get my little pointer out of the way here. And I'm going to click on this to make it bigger so that we can kind of see it. So the idea here is that what you're going to see are the different states of matter that are they're written here, right? So we've got solid, they're in the bold, liquid, gas, and plasma. And the arrows represent what's happening. So is it going from a solid to a liquid, or is it a liquid and it's freezing into a solid? And then the words are indicating the process that's occurring. So if you're moving from a solid to a liquid, it's because the solid melted. If you're moving from a liquid to a gas, it's due to the process of vaporization. If you're moving from a gas to a plasma, um, there isn't a process that's there, but that's the other state, right? And then we have some vocab terms that might not be familiar, endothermic and exothermic. So just remember that endothermic means you add energy. And exothermic means you remove energy. How this might feel to you is that a process that's exothermic feels hot. And the reason why it feels hot is because the thermal energy is being removed from the substance and you are absorbing that thermal energy, so it feels hot to you. And endothermic energy is going to feel cold because, again, it needs energy. So it's going to take the energy from you and it's going to feel cold to you. So does it need energy to get it going? Well, if I'm melting ice, I definitely have to add heat, right? That's why it's endothermic. But if I'm taking liquid water and I have to freeze it, I have to remove some of the heat from the water in order for the molecules to move slower and, it to be able to solidify, and so that's considered exothermic. So that's kind of a, and hopefully helps explain that concept to you. All right. And so let's see, it's talking about observing substances and water and hydrogen bonds. And I'm not going to go through every little detail here because I do want you to read through this. But I do want to go through the math that's involved in this. So the first thing that we have is our heating curve. And it might not look like you expect it to look. Essentially, this is what's happening to the temperature of, in this case, water. As we heat it, it first increases in temperature pretty steadily, right? And again, let's see if I can do this. On the x-axis, we have energy. On the y-axis. So we're adding energy to this. This is something that we're adding energy to. And then at 0 degrees, it stabilizes and it stays that temperature. And this is what we meant by you can continue to add energy or add heat, but there's no temperature change, right? Because we talked about that before, and you're just maybe thinking that makes no sense. But what's happening here is something called a phase change. So here we have a phase change. And what that means is that the energy that would normally be used to change temperature, to make those molecules speed up, because remember, temperature is the average kinetic energy of those molecules, is being used to break the bonds of the ice that's being held together in this crystalline structure. So this particular phase change is melting, right? Now, as soon as all of the ice has melted and there's not even a little tiny morsel of ice left, morsel of ice, is that the right word? I don't even know. Then the temperature continues to increase steadily. Again, you're still adding heat. You've not turned the burner off the stove this whole time. But now you can see that temperature is increasing a very, very linear state, very, very evenly. Oh, but then it hits another plateau right here, where again, temperature isn't changing, but it is absorbing heat. So you have another phase change. And I'm going to give you a second to guess what phase change we're talking about, because we're going from here we have all solid. I don't like that. Well, we're just going to go with the yellow, right? And then as soon as we get to all liquid, we're here. This is liquid. The next state of matter would be gas. So this is evaporation or vaporization. The two words probably aren't exactly synonyms, but they're pretty close. Okay, so that's the reason why we have these flat plateaus on the graph, is due to changing of phase. I'm going to go ahead and clear this off. I'm going to go down a little bit. Now, if the energy is going the opposite direction, as we see here, in this case, it is energy that's being absorbed. So it's going to feel cold. You have to like cool it down, right? So the movement is in the opposite direction here. So again, if you start with a vapor and you cool it down, it will do so in a very linear way until it stabilizes, until it'll be a mixture of a liquid and a gas here. And once it's, so this phase change here, okay, is condensation, because it's just the opposite, right? And once it reaches this point, now it's all liquid. And all of that heat, we're not adding heat anymore, it's cooling down. So it's off the burner at this point. is going to, in a very linear way, decrease temperature until it again reaches a plateau. And this plateau is going to be your freezing. So we can look at this in either way depending on whether or not we're adding heat or heat is being taken away. Okay. So then we get the math. Oh my goodness, there's little q's, there's a little m. What's going on here? All this stuff. So your major formula for this section when it comes to phase change is mc delta t, which is right here. Q equals mc delta t. And I'm going to write that over here as well. Q is equal to mc delta t. You're probably wondering why I even had the whiteboard over there, but that's just because I needed to use it at some point. So in this case, we try to keep our variables the same. In this case, m is mass. It's always been mass, right? And this is in grams, right? Our little q represents the quantity of heat. So I know it seems weird that q is actually joules, but q, so the quantity, it's just wild. Okay. That's our q. M, oh, I did that already. C is something called specific heat. In fact, it's also known as specific heat capacity, which is where I think the C comes from. Now that's a weird one. That's one you're probably not familiar with, but specific heat capacity means the amount of heat that is required to change that particular substance, 1 gram of that substance by 1 degree Celsius, okay? And that is the reason why the units are joules, which is heat, because heat is energy, and energy is measured in joules, per gram degrees Celsius. So the amount of heat, the amount of joules needed to change 1 gram, 1 degree Celsius. So that's telling you what you're doing in the units that go with it. And then delta T is our change in temperature, right? Degrees Celsius. Sorry, my writing is terrible here, but I'm using my finger, so it's kind of hard to do. All right, so that being said, I'm going to clear everything off here. Just going to go back. So this is for water, okay? So every substance has its own specific heat capacity. I don't know if this is going to give us that. Let me see if I can find something. I just want to get you a nice little specific heat capacity. Because, I mean, you can find a bunch of them. I just Googled specific heat capacity table or graph would probably, no, table, a chart, something like that. Well, here's one example. It doesn't have water on it, but it'll kind of give you an idea. This is a specific heat capacity table with like air, oxygen, et cetera, and you can see the numbers, right? So as you look at them, the higher the number, the more heat is required to change its temperature. So it's harder to change the temperature. And as you might expect, the things that are easier to change temperature are usually really good, they are good conductors of heat. So good conductors of heat generally are easy to change temperature on. That means they heat up really fast, but they cool down really fast too. So we're not just looking at like how easy is it to heat them up, but how easy is it to change their temperature in either direction, right? Water has a pretty high heat capacity compared to other substances. If you look here, liquid water has a heat capacity of 4.18 joules per gram degrees Celsius. That's pretty high. Compared to the table that I showed you before, it's higher than anything on this table. This is a lot of of conductors, but kind of gives you an idea. Um, things that are good insulators typically are not good. Sorry, I'm trying to, the tools are kind of, but things that are good insulators usually have higher heat capacity. So you look here, for example, helium has a really high heat capacity. Hydrogen has a really high heat capacity. Kind of makes sense to me because they're very, very lightweight gases. But that being said, you need to pay attention if you're dealing with solid water, it's 2.05. If it's ice, if it's a liquid water, it's 4.18. And if it's water vapor, it's 2.08. So there's different numbers depending on what you're looking at. Okay. It says as long as you're working within a single phase, you can use the formula MC delta T. And then it gives you a question. Can you determine the amount of energy required to raise the temperature of 50 grams of water from 20 degrees Celsius to 55 degrees Celsius? So let's look at that. That should be relatively simple because a lot of these are just, what I would call plug and play math, where the formula is given to you and you just plug it in the numbers. So what we need is, what do we need? Oh, I need my pen to work. All we need is, let's see here. We don't know the amount of energy, so we're looking for Q. That's what we don't know. Q is an unknown, right? We have our mass, and it says in grams, so we don't have to convert anything here. Grams is what we're looking for. We have our delta T. That's going to be, it's going from 20. So remember, delta T is the final temperature minus the initial temperature. So delta T would be equal to final minus initial. It's always final minus initial. And we have the specific heat capacity. So it's just regular old water. It didn't say there's anything else. It's like that's within the realm of liquid. Okay, so let's do some solving. So Q is equal to 50 grams. I love this whiteboard, but it likes to correct my really messy writing and make it things like triangles when it's not supposed to be. Okay. Times, what did we say the heat capacity was? I think it's 4.18. Okay. Times. Wow. And that's joules per gram Celsius degree. And we're going to get rid of some of the stuff over here just because it's in my way. Okay. And then we also need delta T. So delta T was 55 minus 20. Okay. So first thing I'm going to do is just solve what's in parentheses. So 55 minus 20 is 25. So take 25 degrees Celsius here. Multiply that times that 4.18 joules per gram Celsius degree, and then multiply that times the 50 grams. And I want to cancel out some of these units here. Let's see. So grams cancel, Celsius degrees cancel, and all we have to do is multiply across to get our answer in joules. So it should be 50 times 4.18 times 25, or 5,225 joules. Okay, so let's see what it says here. Let's see what it says for an example. Does it give me the answer? It would have, but I can't do math, so we're gonna go back and change this to 35 because I just did that wrong. Okay, so let's try that again. Let's see. Yeah, 7,315. There we go. go. And that's one of the reasons why I want you guys to show your work on tests as well, because then if you make one little tiny dumb mistake, you wouldn't get penalized for the entire thing. All right. So let's see here. It says energy is also absorbed when water undergoes a phase change. So on graph 1, if going from point A to point B, you will notice that the temperature does not change, even though energy is being added. We mentioned that. At point A, 0 degrees, which is the melting point, water is completely solid. As energy is added, the ice gradually melts until it reaches point B, where the melting is completed and the substance is completely liquid. At points A and B, water coexists as both solid and liquid. The energy required to melt this is known as the heat of fusion. That's what the H sub FUS means. So that's the energy required to melt, the heat of fusion. For each gram of ice, 334 joules of energy must be absorbed in order for it to melt. When ice melts, the hydrogen bonds that give it shape are broken. It's the remaining of these bonds that absorbs the energy. The amount of energy needed to melt ice, assuming it's 0 degrees, can be found by the following formula. So because it's contingent upon how much water you have, you essentially just need to know how much water you have. So the amount of heat needed is the mass of water times the rate of fusion, which we said was 334 joules per gram, right? So if we have 75 joules, can I erase the entire screen? Simple, guys, this is simple here. So it's basically that 75 grams times the 334 joules per gram. So again, grams are going to cancel, so you're just taking the 75 times 334, which gives us 25,050. Let's see if that's right. It is. Way. And then it just says here we have a different heat of vaporization. So it requires more heat to vaporize water than it does to melt it or freeze it or whatever. It's changing for the fusion. I guess it's going, it's melting. So if it's going from a liquid to a vapor, it needs 2,260 joules per gram. Okay, so let's make sure you have that stuff written down, you guys. You want to make sure you have that. So the heat of fusion is 334 joules per gram. And the heat of vaporization is at 2,260 joules per gram. So it's going to take more energy to vaporize stuff. And it's the same process otherwise that we did before. Okay. All right, so then on this next page, it's saying, well, how do we calculate the amount of energy required to take some, I think in this case, talking about 80 grams of water. Let's see here. I'm sorry. I want to make sure I'm saying it the right way. Okay, so this is solid water, ice, right? You have 80 grams of ice. It's negative 20 degrees Celsius, and you need to change it to 150 degrees Celsius, which would be a vapor. Want to know all of the energy required to do this process. So what you need to do is you got to break it into steps. So the first thing you're going to be doing is you're just changing its temperature from negative 20 to 0. So that's this portion. Because here it's changing temperature, right? So from negative 20 to 0, and let's see how much, I don't remember how much, we had 80 grams. Okay. Right there. So we have the mass is equal to 80 grams. Okay. And in this case, we're just going to use MC delta T, our original formula. So we do know that this is ice. And I don't think it's on this page anymore, but they may actually show it here. Yeah. So remember that the specific heat of ice was 2.05 grams or joules per gram Celsius degrees. So we're going to take the mass of the ice, 80 grams, times the specific heat of ice, times the change in temperature. And it went from negative 20 up to 0. So that's a 20-degree change in temperature. So I did that part in my head just to make my make it a little less messy here. So then we're going to multiply all that out, and they did that for us over here. That's the 3,280 joules. Okay. And then the next step here is to make sure that you're taking into consideration this here, because the temperature is not changing, so you can't use MC delta T. You have to then use the heat of fusion, which is this equation. So we're going to use that Q equals M H fuse here. So M again is 80. And the heat of fusion was that 334 joules per gram. And you have to get that is equal to 26,720. Now, those are just the first two steps. I could sit there and go through this whole thing. It goes through the whole thing with you, but that's kind of what we're doing in this problem. And you'll probably end up seeing something like this on your unit test. You're going to have to add up all of these different components, like the amount of heat to go. I can't get it to stay back to where it was. That sucks. So, okay. So the amount of heat here, 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 and here. Wherever you have a flat plateau is we're going to use that Q equals M and the heat of either vaporization or fusion. And wherever you see the ramp or the I don't know, like the positive slope there, you're going to be using the MC delta T equation. So hopefully that makes sense. Okay, and then you got some check-in questions, and it talks a little bit about endothermic and exothermic, which we kind of already talked about in the first couple of slides. Hang on a sec. I just want to make sure I don't miss anything. Nope, we kind of went through this already. So if you have any questions on this, let me know. Otherwise, hopefully it made some sense and it does help a little bit, and I will see you guys in the next lesson.